My name is Mark. I'm a data engineer at Shopify. And in this talk, I'm going to recount a project that I worked on at Shopify where we migrated petabytes of data to Apache Iceberg format using Trino as a compute engine, which is, I think, what makes this project a little bit more interesting or different than maybe some other migration projects. So let's go over the agenda. So first, I'm going to kind of set up some context of why we wanted to do this. No one in their willingly migrates petabytes of data. It's actually kind of hard to do. So why did we want to do it? How did we get there? Why did we choose Iceberg as what we were going to migrate to? I'm going to briefly go over some migration strategies that if you find yourself in the same position, you would want to consider. I'm then gonna kind of go over the Trino Iceberg connector, like its integration and how that evolved over the course of our project. I'm gonna show you guys some benchmarks of the pre and post migrated datasets, and then I'm gonna finish off with some reflections about the project and things I might do differently if I was to do it again. So let's start off with some context. So I'm on the Lakehouse team at Shopify, and we have two generalized mandates. We are mandated with ingesting all our first-party data, but also we're in charge of the lifecycle of data on disk. And so I'm focusing on the storage layer, so like the lifecycle of data on disk. And initially, our team was really focused on this one class or bucket of data called raw data, which had three main subdivisions, which were event data, CDC or change data capture data, and third-party data from maybe we're using HubSpot or something like that that we want to ingest into our warehouse. Because our team was initially focused on this data source, most of these actually use rational table formats. Most of them are in Hive table format. But as our team matured, we kind of realized that we were missing a large chunk of our data sets at Shopify, and that was our model data. And as we kind of looked at these data sets, we kind of found that there were a lot of silos between the data sets that were determined by the tools that were built to work with the data themselves. So we found that there were tools that were specifically built to work on top of Spark. There were tools that were just raw SQL, and then there was also tools built on proprietary engines like BigQuery. And when we kind of pulled back the layers here, we actually found kind of like a horror story. A lot of these tools actually invented their own table formats. So they invented what they would consider a data set or a table to look like. And as one might think, this made interoperability between data sets really, really difficult. And so if I wanted to spin up a new tool, I actually first had to do is build adapters into that tool so that it could actually interpret what a data set from other tools were meant to look like. And so this made our code really bloated. It made it complex to maintain. And you just have it's just doesn't really scale that well. So even worse than that is data scientists would come to us and ask really simple questions like, hey, I used tool one, I produced a data set, I want to use that as input to another tool. How do I do that? And we're kind of like, that's actually really hard. So, something had to change. We wanted to re-architect our data lake and make that the kind of the central layer where all data came in and out of, and produce a specification that all tools would use to store their data on disk. And so, we decided we needed to determine what kind of open table format we wanted to use. And we already had some in-house experience with Iceberg. And one thing that was really nice is because we had so many different tools at the company that were reading and writing data, Iceberg actually produced a specification which we could give to other teams that they could build their tools adhering to, which means that although we weren't ready on day one to adopt Iceberg, if we there's a spec that we could all build towards, and at the end we would know that we could come together and our tools could all talk to each other. So, we're at Subsurface, so I'm sure a lot of you already know what open table formats are, but just to go over it really quickly, it really is just a library that keeps track of files that comprise a table. And so when I first started learning about open table formats, I kind of got confused about this because it's an abstraction, really. And one colleague came up with a really useful example that made me really like click for me. And what she said is that it's like a file system is to a hard drive is like Iceberg is to an object store. So you have your file system, you have a file that you're interested in looking at, and you go to open it. You don't have to know where that file is stored on disk. That's the power of the abstraction that the file system provides you. It's the same thing with Iceberg. You want to, select star from a table. You don't need to know all the files that you need to read now on your object store. That's the abstraction, the power of it, the power of the abstraction that Iceberg gives you. So you don't need to track that anymore. And so, as I said, there's like way better and way more extensive talks on Iceberg here. I just want to like show you guys the Iceberg spec, the diagram. And I think the only real important thing for my talk is that there's a metadata layer which points to your data files. And that's all I really want to go over. So at Shopify, I don't want to take too long on this, but just getting to this point where we were able to convince senior leadership that this was a problem, that this was the right layer to solve the problem, was a huge endeavor and something that took a lot of time. However, once we got there, people were a lot more excited to write new data, but what's actually holding you back is compatibility with your old data. And so this is where you kind of go like, oh crap, okay, now I need to migrate my entire data lake to this new table format. Okay, so to go over the agenda real quickly, we have gone over the context. I've explained why we decided to go with Iceberg, and now you have to do your migration. So to do our migration, we decided that we were going to first focus on one subset of our data. So as I said, in our raw data bucket, most of our tables were already stored as Hive tables. But one thing that's really sad is that the file format was actually in JSON. And that will be more important later. But now that we've identified one data set or a class of data sets that we want to first migrate, we have to start thinking about the different migration strategies. And this depends on what your current state is. If your data is not in a supported file format, then that means you're going to have to restate or rewrite everything. If your data is in a supported file format, but you want to change the partitioning strategy, so how it's organized on disk, then again, you're going to have to restate or rewrite all your data. If you're in the lucky position where your data is in a supported file format, for Iceberg, that means your data is in Parquet, Orc, or Avro, and it's properly partitioned, well then you're actually in a really good spot because this means you can get away with only generating those manifest files and you don't have to restate any of your data, which is the real time consuming and expensive part. So as I previously mentioned, our data format was actually JSON. So this meant that we had to rewrite everything. So we came up with a system that would kind of rewrite our data. We decided that we would have this table manifest file. We would chuck that into a DAG generator, kind of like dynamically generate DAGs based on that table manifest. And you would get one DAG per table. If we blow up into what one DAG actually looked like, it had three basic steps. It filled a queue with all the partitions to be rewritten. And then we had a worker, which would, like in that process, that would take a partition off the queue and rewrite that data using Trino. We would then reconcile the partitions using Trino as well. So we would do like counts between our old and our new data. If they didn't match, we would drop that partition and try again. Basically, what Trino is just doing, though, is it's reading data into memory, and then you're writing it down in Iceberg format. So now that we've gone over a few different migration strategies, I want to take the next little while to talk about the Trino Iceberg integration. What was really interesting about this project was we were actually like developing our project when the Iceberg connector was being developed in Trino. So we hit a lot of the first roadblocks, I think, and reported them. And what was really cool was that the Trino community was really quick to address our concerns and fix all the bugs that we were finding. So in our current setup, we found that for our larger tables, it was going really slow. You know, you have your queue, you have your worker is just taking partitions off one by one and rewriting one by one. So I think if most developers found themselves in this case, they would just think to, scale the number of workers or increase concurrency of the process. So you have n workers pulling off of the queue at different times. And so that's what we did. But when we did this, we actually started getting this error a lot. We got commit failed exception. And you can read what's happening, but I'm going to explain it with some diagrams. So let's say we have two processes that are trying to make appends or any changes to your Iceberg table. Well, in Iceberg's snapshot model, what it does is your snapshot model has to increase sequentially. So your metadata, if you decide to append to it, it needs to reference the snapshot ID that's previous to it. And so if one of your processes succeeded and then your other concurrent process tries to append to it, it actually isn't referencing the head of your table anymore. And so you'll get that exception. This is something that's changing in Iceberg. It's changing in Iceberg as it evolves. But at the time we were doing this project, it was still in this model. And Iceberg also allowed you to do something called a commit retries, which meant you didn't have to rewrite your data files. You could just regenerate your manifest files, which is a really lightweight operation, and reference the new head of the table. But what had to happen is you had to throw the proper error so that you could make use of Iceberg's commit retries. And that's what was patched by Alex Joe. In May of 2022 in this PR and was in the release of Trino's 379 release. What was kind of interesting about this is that Alex the PR wasn't actually entirely focused on this bug. He kind of just patched it as he was working and you see it as a commit message through proper exception. And I don't know if he realized how much help that would have been at the time, but it totally unblocked our project. So that was really nice that we could now scale our writers and really rewrite data at petabytes of the scale. So another issue that we started running into a lot was this thing called the missing file problem. And, one second. Yeah, so the missing file problem. And what this actually showed was that once we started writing in Iceberg, there would be files that Iceberg thought were part of its manifest in this case, or in its in its manifest, but they actually didn't exist on GCS or whatever your object store is. And so what was happening here was that Trino was writing to the Hive Metastore, doing the Hive Metastore reference, but the connection between Trino and the Hive Metastore actually was severed. And so it didn't know if its commit actually succeeded or failed. And Trino was trying to be nice. And so it was trying to be nice. And so it said, I don't know what the result of my commit was. So I'm going to go and proactively clean up the files that I just wrote. The only problem is that the commit actually succeeded. The data files and the manifest files were actually included in the Iceberg table. And so now, after Trino went back and cleaned up after itself, your table is corrupt and it can't actually read any of the data. And so this was patched by Marius Grama in September of 2022. And basically what happened in this PR is that they just avoided the proactive file cleanup on the Hive Metastore timeout. And this is really the approach that most engines are taking these days. And it's because Iceberg comes with out-of-the-box orphan file cleanups. So having files that aren't actually included in the table in your object store isn't a big deal. You can just go back after the fact and clean it up. So might as well just keep them around. Okay, so we've gone over context, why we chose Iceberg, different migration strategies, and I just finished going over some of the most interesting changes in Trino Iceberg integration. Next, I'm going to go over some benchmarks of some of the data sets that we migrated. So this first data set, as I said, I work at Shopify. Shopify is an e-commerce platform, so we host a lot of different stores, and people buy things from those stores. So we have one table, which is all the orders of all the stores at Shopify. That table is 160 terabytes in size, and I decided to just make some contrived examples, building like models on top of that table. I ran these queries with 60 N2 standard 64 workers and used Trino, obviously. So we can see that the migration from Hive and JSON to Iceberg and Parquet really improved the planning time. We can also see that the memory pressure on Trino itself also was greatly reduced after these migrations. But maybe in like a practical sense, the most important thing is that the execution time went down. The execution time of the query that I ran went from taking 1 hour to 3 minutes. And I know this is like probably like really like a big deal, but I always just like to think of the data scientist. They submit their query, they're looking for data, they're in their flow state. But then they have to wait an hour. That's going to break their flow state. They're going to, go on their phone, go do something else, break all that context. Then they're going to have to come back and, look at the results of their query. Now that it takes 3 minutes, they can stay in that flow state, and it greatly improves the speed that they're able to innovate, which is, why I like being a data engineer. So it's really, really rewarding seeing these results. I decided to build a little bit more complicated of a model, and I decided that I wanted to see what stores had the most checkouts in the past month. So I wanted to basically see what our best stores were in the past month. You can see planning time also went down, memory again went down, and execution time went from about 30 minutes to about 2. So the last benchmark that I'm going to share with you is actually one of our biggest tables. So Shopify has this query API, which we expose to any developers if they want to build applications on top of Shopify. This table is about 1.5 petabytes. Actually, it's a little bit larger, but who cares? And I decided that I wanted to know what were the most popular schemas or endpoints on this API that people were using in the past month. So we can see that, again, planning time greatly improved, cumulative memory greatly improved, and execution time goes from 180 or 1800 minutes to 1.78. So this is the difference between, submitting a query and like going to sleep versus submitting the query and getting it almost instantly. So those benchmarks kind of like speak for themselves, but we're going to go over some reflections that I have of completing this project and maybe some things I would do differently if I was to do something like this again. So, we just went over the benchmarks. Using a modern table and file formats significantly improves query performance, and I think that's kind of like a no-brainer. One thing that I was really depressed about in this project is in our initial design, we decided that we were going to write our old data and our new data to 2 separate tables and that we would stitch them together via views. Unfortunately, right now in Spark, you can't have something like an Iceberg view. They're not supported, although that is changing in the near future. It wasn't supported at this time. And so it was the last step of the project, and we found out that it actually wasn't possible. It was really depressing. So what we ended up thinking of doing was that we were going to just like write to the same table, and that would kind of like prevent all these issues. The next thing I'd recommend doing is constructing a migration priority list. So like the benchmarks, with the speed improvements, you'll have some data scientists that will come to you and be like, oh, I don't want to wait an hour. I want to wait a minute. And so you'll you'll prioritize their data sets that they want to move. But there's going to be a large class of data scientists that have their jobs running overnight on a schedule that don't really care if it takes like an hour or 2 hours. But people who will care are the people who operate your query engines, because this means that they'll have a lot less load on their platform. So using that information, like the load on Trino, we constructed a priority list for the data sets that we would have the biggest bang for our buck if we migrated. As I said, the Trino Iceberg integration is quickly evolving. And so one thing that we had to get really good at is redeployment tooling. So if Trino came out with a patch or a new feature, I wanted to get my hands on it right away. So I kept being like a nuisance to the Trino team and being like, can you redeploy Trino with the newest version? So getting really good at this redeployment was really important for us. The last thing is kind of a tangent, but I kind of think, daydream about alternate ways to rewriting history. Rewriting petabytes of data is really time consuming and costly. And so you might think that like as data gets older, it actually gets queried less and less. So maybe you don't actually need every single row. Maybe you can get away with like summarizing your historical data in terms of like distributions or something like that. And then instead of rewriting every row, you just like have a summary of that data that can be used in your queries. So that's kind of something I've been thinking about a lot lately. So lastly, I just want to acknowledge the other people that worked on this project with me, Sam Weeding and Victoria Bukta. And that brings me to the end of my presentation.